All right. Good morning, everybody. Sorry we had to do it this way. I just kept pushing, telling myself I wasn't sick and not resting. And that happens, then you actually do get sick. So, all right. So, this summary page I think is really useful I don't always do this for the chapters, but because this one is a little bit different because there's so many concepts, it's hard to know what exactly the expectations are. I've done this for this chapter to hopefully make it clearer. So, the first thing is that we have the big concept things. So, we have this idea of the electron simply thought of as a particle. And I would say, even before that, we have light thought of as a wave. And then we start thinking of it as also a particle. So this is the idea of photons. And as part of that, we need to be able to calculate wavelengths and frequencies, and then also energy. Okay, so you will be expected to do those types of calculations. Then when we're talking about the electron specifically, we take the same idea of it was originally a particle. Using the emission spectra, we verify or predict that the energy of the electrons was quantized, which leads to the Bohr model and the ability for us to calculate the different energy associated with transitions in the Bohr model. So remember these N values, those are like the energy levels. And so if you're going from a high one down to a low one, you can plug in N equals 3 for your initial and N equals 1 for your final, and that will give you the energy of a given photon. Okay. Ultimately, that one didn't work out so well. And so we continued to have postulations on how we could improve this model. And so just like with light, we were able to start incorporating this idea of wave-particle duality. So up here, that's what we called this for light, was wave-particle duality. And now for the electron, we're starting with the particle side and going to the wave side. And treating the electron not only like a particle, but also like a wave. Okay? That led to our modern understanding of quantum mechanics. And the results of the quantum mechanical equation gives us quantum numbers that define the energy and the position of each electron in an atom. Okay? So you have to have a distinct N, L, M sub L, and M sub S for every electron in an atom. When we list these three at least, that's going to give us the orbital that the electron is in, which is basically the region of space where the electron is predicted to be. Okay? So now we're going to go through, the rest of today is going to go through practice problems, applying this. And they're actually, when I was looking through them, don't seem particularly complicated because we are going to continue this as we move into chapter 9 on Wednesday. So I think they're very similar to the things we've done before and just getting, more of them. The other thing I would say is since we're doing class virtually, I would be happy. Ideally, you guys would be able to view this early in the day, start working on your homework today and into tomorrow, and then email me with questions as they come up for the homework. And then I can always post additional videos that are kind of follow-ups to this lecture. Okay? All right. So what we'll do is I'll show you the question, you pause the video, then you come back. Don't just watch me answer the question. That's not useful for you. So pause the video at this point, complete the problem, and then come back and watch my solution. Okay, so now, hopefully you've done this already. List allowed values of N. So n can be any integer, 1 and beyond. It doesn't have a restriction because it's not dependent on any other quantum number. The lowest, the n value that's lowest in energy is n equals 1, which is also the n value that's closest to the nucleus. Okay. Next question. Go ahead and pause. Okay. For each n value, 1 through 4, list allowed values of L, both numerical and letter designations. So I'm going to write this as kind of a chart. N equals 1, n equals 2, n equals 3, n equals 4. So if you remember, L values are a range from 0 through n minus 1. So for n equals 1, L would have to be equal to 0. There's no other options, and we would call this S. It defines the shape. It defines the shape of the orbital. In n equals 2, L could be equal to 0. It could also be equal to 1. So this is S and P. For n equals 3, L equals 0 or S. L could be equal to 1 or P. L could be equal to 2 or D. Remember, these are all possibilities, but for a given electron, you would have to pick a specific N, a specific L, a specific M sub L, etc. And then for 4, as you might expect, we just add one more. So every energy level you go up, so I'm referring to these as energy levels or shells. Every one of those that you go up, you add an additional L, possible L value. Or another way of saying that is that you have another orbital type that has a different shape. Not just a single orbital, because the number of those might be different, but a different orbital type or shape. Okay, let's go ahead and pause here. Okay, when you combine the N and the L value, this is called the subshell or sublevel. Each subshell has a different energy. For the subshells up through n equals 2, for the sublevel up through n equals 2, n equals 4, indicate the possible M sub L values. So it shouldn't say up through, it should say in n equals 4. So hopefully when you pause that, you are able to either see that or start watching. So if you want to pause it again at this point, if you were confused by that, feel free, obviously. Okay, so now what we're going to do, I'm just going to copy these down because it said for n equals 4. For each sublevel in n equals 4, indicate the possible M sub L values. And in addition, I think what I'd like to do is actually, I'm going to refer to these, but I'm going to rewrite them as its own little chart just to be really clear, to make it a little easier to understand. And I'm going to write them with their sub-level designation. So by this, I mean if n equals 4 and L equals 0, I'm going to write 4S. For n equals 4, L equals 1, I'm going to write 4P, and so forth. 4D, 4F. then they want me to indicate the M sub L values for each of these, okay? So for the 4s, if you remember, M sub L is also a range from negative L to positive L, okay? So if L is 0 for 4s, the only M sub L value we can have is 0. Negative 0, which doesn't mean anything, through positive 0 also doesn't mean anything, so just 0. For the 4p, the value of L is 1. So M sub L could be negative 1, 0, or positive 1. For D, which is L equals 2, negative 2, negative 1, 0, positive 1, positive 2. And then finally for F, where F equals 3, an L value of 3, negative 3, negative 2, negative 1, 0, 1, 2, 3. Okay, hopefully you're starting to see the patterns, and so hopefully it isn't too difficult as you start to see those patterns. And then just this note, each of these M sub L values within a subshell is called an orbital and can hold 2 electrons with either the value of plus 1/2 or minus 1/2 for the M sub S. So like you're going to have 2 electrons in each one of these. So another thing that tells you is the total number of electrons that can be held in N equals 4. So this one would have 2 electrons, this one would have 6, 10, and 14 for a total of 32. And the trick with that one is you can also do this if you haven't written all this out. You can say 2 times N squared. So 4 squared is 16 times 2 is 32. So we call that the electron capacity. Okay, next question. Go ahead and pause. Okay, how many M sub L values are possible for the 3D subshell, sublevel? I usually call these subshell. Okay, 3D means N equals 3. D means L equals 2. And remember, M sub L should be negative L through positive L, or negative 2, negative 1, 0, 1, 2. So 5 M sub L values, meaning that the 3D subshell has 5 orbitals in it. Okay, second question, is it possible to have an L of 5 when N equals 5? No, because L is 0 through N minus 1. So if N equals 5, the highest value of L would be L equals 4. Okay. Next one. Let's see how many more of these we have. 3 more pages. Okay, go ahead and pause there. Okay. What are the possible L values when n equals 6? Hopefully you're kind of getting this here. This is going to be 1, 0, 1, 2, 3, 4, 5, or S, P, D, F. We haven't talked about this really, but if you continued on the letters, it would just be G, H. They just go F and then go on. Specify the number of orbitals in the highest L value, so that would be this one, when n equals 6. So an L of 5, the number of orbitals corresponds to the number of M sub L values. So M sub L here would be -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. So 11 orbitals. The other way you can remember this is that each additional L value, erase these letters here, each of these additional L values, the M sub L goes up by 2, and they're all like odd numbers. So this one is 1, 3, 5, 7, 9, 11. Or I think there's like a formula, it would be like 2L plus 1. So 5 times 2 plus 1 would be 11. Okay, so just a few different ways to remember that. I prefer just like writing them out to verify based on this whole what are the allowed values. Okay, go ahead and pause here. Okay. So here, the consider the sublevel designation n equals 2, L equals 2, sorry, n equals 5, L equals 2. What is the sublevel designation? So that would just be 5 when L equals 2, that's D, so 5D. What are the possible M sub L values for this? Again, L equals 2. So M sub L could be -2, -1, 0, +1, or 2. How many orbitals are in this sublevel? 5. Ooh, and this one's going to be a little longer. Give the N, L, and M sub L values for each of these orbitals. It says in the table. I don't think I have a table there. Oh, well. This one's probably not the longest. That's going to be the longest. All right. So I'll make my own table. N, L, and M sub L. And this is for 5 different orbitals. So I'm just going to say 1, 2, 3, 4, 5. Because I know there are 5 orbitals. So n equals 5. That means every single one of these has an n value of 5. L is equal to 2. So that means each one of these has an L value of 2. And then the M sub L is what we listed up here. -2, -1, 0, 1, 2. Okay? All right, last one. Okay. Draw all the subshells and orbitals for n equals 5. What will be the electron capacity? Let's go ahead and just use the formula 2n squared to start here, and then we'll come back to it and verify that. So 5 squared is 25, or 50 electrons. All right. So for n equals 5, let's pretend you know all the values here are 5. L could be 0. And the M sub L there would only be able to be 0. L could be 1. And that would have an M sub L as -1, 0, or +1. So I'll just go ahead and write that for each of these. And maybe I'll go ahead and write the N value of 5 as well for each one of these orbitals that I write. So it's like a complete chart. Okay. Then the next M sub L value would be 2. Oh, this is going to be so long. I just realized. The M sub L value with 2 is going to be -2, -1, 0, 1, 2. Okay, so each of those is going to have an L of 2 and an N of 5. Try to squeeze a little bit more, and then we'll like go to a second chart here. L, M sub L. Okay, so next one would be 3. And that could have an M sub L of -3, -2, -1. I'm going to switch over here, 0, 1, 2, 3. Now these are all values of L, where L equals 3. And N is not changing. This is only for N equals 5. There's a lot of orbitals once you get to N equals 5. Now, final L value would be 4. So the M sub L could be -4, -3, -2, -1, 0, 1, 2, 3, 4. All of those with an L value of 4. And an N value of 5. Now, the way we can verify our electron capacity is to know that each one of these can have 2 electrons, one with spin +1/2, one with spin -1/2. So if we count up each of these orbitals, we should get that times 2 should be our electron capacity. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Times 2 is 50, which is what we have up here. So certainly if you're asked the electron capacity of a high energy level or a high shell, knowing this equation would be useful so you don't have to actually write all of these out and figure out how many orbitals there are. Okay? I guess just real quick, one shorthand way of doing that is if you had N equals 5, You could write out the N value, the L values, 1, 0, 1, 2, 3, 4. And then you could just write out how many M sub L values there are. Because like I told you before, they go in odds. Then if you add all of these together, that's 25 times 2 for the number of electrons, or 50 electrons. So just a few different ways to do a question like that. Okay? All right, that's it for today. Homework due tomorrow night, and then also the reading for chapter 9, which is our last chapter. So we'll go ahead and cover that starting on Wednesday. And then keep in mind, we're, moves pretty quickly, but we're on to our next test will be a week from Friday. So still a good 2 weeks of class, but a week from Friday, which is the day before Thanksgiving break. Okay? Please do not ask me if you can, take it early or late. If you're just traveling for family travel, you really should. You have an entire week off for Thanksgiving. So you should be leaving your family travel until after you're done with your classes on Friday. Okay? Thank you.